And how about the shape of alkanes? What do they look like in 3 dimensions? We can have different shapes known as conformational isomers. I put isomers in quotes here because these are not isomers in the traditional sense of isomers that are non-interconvertible unique compounds. Conformational isomers, also called conformers, are actually can be interconverted, and so that's why I prefer not to call them isomers. I prefer to call them conformers instead. And the way they are related is they are structures which differ only by rotation about sigma bonds. Okay, so conformers are different forms of the same molecule. And they are interconvertible because the way we go from one to the other is simply by rotation around a sigma bond. So for example, conformations of ethane, if we take a look at an ethane molecule, we have just a 2-carbon structure, CH, this is a CH3, 1, 2, 3, this is a CH3. The various conformations that ethane can have are these. We can simply rotate around this carbon-carbon bond, and in doing so, this molecule is going to have a different 3-dimensional shape. And the relationship of, let's say, this conformer to this conformer they're called conformational isomers or conformers. And so I have shown here examples of 2 extreme conformations. One conformation has 2 hydrogens pointing up in the same direction. And if we rotate this just 60 degrees, we'll see in our 3D sketch that one hydrogen is pointing up and one is pointing down. Or we can rotate it this way and get that same conformation where one hydrogen is up and one hydrogen is down. We have names for these conformations. When the 2 hydrogens in the plane are pointing up, we call this the Eclipsed Conformation. And when one is up and one is down, we call this the Staggered Conformation. Okay, and these are rapidly interconverting conformers. So these are not 2 different molecules. It's simply one molecule that's rotating around very rapidly. Now, one way that you can really see why we call these eclipsed and staggered conformations is when we view the molecule not sideways like we did in the 3D sketch, but we view it in this way where we're viewing down the carbon-carbon bond. Okay, and when we do that, now the way we're going to see the eclipsed conformation is when the 3 groups in the front exactly align with the 3 groups in the back. So this has one, straight down, or they both have one straight down, or maybe they both have one straight up. We call this eclipsed conformation, just like a solar eclipse or a lunar eclipse, or when these things line up with one another. Okay, and the staggered conformation is when you have the bonds in the back are kind of intersecting the bonds in the front. And so it goes front, back, and they're staggered that way. This point of view is called a Newman projection. It's a very valuable projection. The way we can see that is by kind of standing over here and viewing the molecule like this, looking down the C2, C3, the carbon-carbon bond. And what do we see on this front carbon? On this front carbon, we see a hydrogen pointing straight up. And then we have hydrogens down. One is to my right. If I'm looking here, the wedged bond is to my right, and the other one is to my left. So this is what we see on the front carbon. And what do you see on the back carbon? Well, the back carbon, you see the exact same thing. There's a hydrogen straight up, and then the other 2 hydrogens are down and to the left and right. Now, the way we show the back carbon in a Newman projection is we draw it as a big circle so that we can see them both. So this is the back carbon, and this dot is the front carbon. And the back carbon in this eclipsed conformation, we recognize that the back hydrogen is exactly behind the front hydrogen. But what we do is we tilt it just a little tiny bit so that we can see it, so it's visible. So we in our drawing, we move it slightly, but we keep them very close to each other because we recognize that they are, in fact, exactly aligned. So this is what the eclipsed conformation looks like in a Newman projection. If we rotate the front carbon slightly like we did here. So we rotated around this carbon-carbon bond to get this structure. And now, by rotating it 60 degrees, we take this front hydrogen and move it 60 degrees. We'll do it clockwise. This front hydrogen, all three groups rotate as we twist the molecule. Then what happens now is on this front carbon, when we take this same perspective, now on the front carbon we have a hydrogen pointing straight down. And the other two are up and to the right and left. On the back carbon, we see a hydrogen pointing straight up. And then the other hydrogens are down and to the right and left. And so here we see the staggered conformation, a little easier to see in this Newman projection. Now, are these conformations equal in energy? They're not. The eclipsed conformation is higher in energy. It is less stable because of the interactions between the electrons in the CH bond in the front and the CH bonds in the back being perfectly aligned. We get some interactions there. We call that a torsional strain. In having those groups aligned, and when they are spread out, we have a staggered conformation, which is lower in energy. Okay, so while the staggered conformation is lower in energy, again, this is just rapidly rotating, freely rotating around quite easily. Let's call this eclipsed conformation A and the staggered conformation B. And what we can do is we can trace the energy of this molecule as it goes